The floor trembles before the machine moves. That is the first thing men learn when they are assigned to Bay 7. Not the safety protocols, not the shift schedules, not the names of their foremen. The floor trembles first. A low, subsurface vibration that travels up through the concrete, through the soles of steel-toed boots, through the bones of the ankle and the tibia and the knee, and it tells you, before your eyes confirm anything, that something of enormous consequence is about to happen. Then the ram descends. It weighs 400 tons on its own. The total system, the frame, the hydraulic columns, the die sets, the bed plate bolted to a foundation sunk 14 feet into the earth, reaches 2,000 tons. When it closes at pressures that exceed 50,000 pounds per square inch. It does not cut metal. It does not weld metal. It does not coax or persuade metal into a new configuration. It erases the memory of the material entirely. It takes an aluminum billet, a cylinder of aerospace-grade alloy weighing several hundred pounds, and in a single decisive stroke, it compresses that billet into a geometry that did not previously exist in nature. Flanges, spars, bulkheads. The structural skeleton of machines designed to leave the planet. This is a forge press, not a stamping press, not a punch press. A forge press? A distinction that matters because forging does not merely shape metal. It realigns the internal grain structure of the alloy at the molecular level, producing a finished component, denser, stronger, and more fatigue-resistant than anything cast in a mold or machined from plate stock. When engineers at North American Aviation needed structural members capable of surviving the thermal and mechanical stress of rocket-powered flight, they did not turn to foundries. They turned to machines like this one. The men who operated it worked in heat that routinely exceeded 100 degrees Fahrenheit at the die face. They worked with transfer equipment, tongs, manipulators, overhead cranes, that moved billets heated to 700 degrees through a space where a single misalignment could trap a limb between surfaces, closing with the force of a small mountain. Between 1955 and 1972, at facilities operating presses of this class across Ohio, California, and Pennsylvania, dozens of operators sustained crush injuries. Several lost hands. A smaller number did not survive their shift. The parts they made flew anyway. Some of them flew to the moon. That is not a redemption story. It is something harder to name. A transaction conducted in flesh and aluminum and national ambition, the terms of which were never fully disclosed to the men who paid the highest price. This is the account of that transaction. There is a question embedded in the existence of this machine that industrial historians have never answered cleanly, because the answer requires holding two truths simultaneously, truths that resist each other the way two magnetic poles resist contact when forced together by an outside hand. The first truth is this. The 2,000-ton forge press was one of the most productive industrial instruments in American manufacturing history. During the 2 decades spanning 1955 to 1975, large-scale hydraulic forge presses operating at facilities across the industrial Midwest and Pacific Coast produced structural components that were irreplaceable. There was no substitute process. No alternative technology in that era could produce an aluminum or titanium alloy forging of the size, density, and internal grain integrity required by the aerospace industry. The Atlas rocket, the Titan II, the Saturn V, the Apollo Command Module. Each of these programs depended, at some point in their material supply chain, on parts that had passed through the die cavity of a press operating in this class of tonnage. When NASA's Marshall Space Flight Center published internal material specifications for primary structural members, those specifications could only be met by forgings, and forgings of that scale could only be produced by machines of this size. That is the first truth. The machine was necessary, not merely useful, necessary in the strict engineering sense of the word. The second truth is recorded in OSHA incident logs, in workers' compensation filings, in the quietly settled civil suits that accumulated in the court archives of Cuyahoga County and Los Angeles County and Allegheny County across the same 2 decades. The 2,000-ton forge press was extraordinarily dangerous. Not dangerous in the ambient background sense that all heavy industry carries some statistical risk. Dangerous in a specific, foreseeable, and frequently unreported way. Dangerous because of the gap between what the machine demanded of the human body stationed beside it and what the human body could reliably deliver across an 8-hour shift, across a 40-hour week, across a career measured in years. The paradox is not simply that a dangerous machine made important things. That description fits hundreds of industrial instruments across human history. The paradox is narrower and more disturbing. It is this: the danger was not incidental to the machine's productivity. It was structurally connected to it. The speeds, the temperatures, the physical proximity required of operators, the compressed decision windows inside each press cycle, these were not flaws that could be engineered away without compromising output. They were, in many documented cases, accepted as the operating condition. The risk was not an accident waiting to be fixed. It was a variable that had been calculated, weighed against production targets, and permitted to remain. America needed parts. The press would make them. The men beside it would absorb what the machine could not. That is the question this account pursues. Not whether the achievement was real, because it was, but whether the architecture of that achievement was ever honestly examined by the institutions that commissioned it, celebrated it, and then moved past it into the next contract cycle without pausing to read the names on the incident reports filed in the weeks before the launch. To understand why machines of this scale were built, it is necessary to understand the specific character of American industrial anxiety in the years immediately following the Second World War, an anxiety that was not the anxiety of defeat or scarcity, but something more peculiar and in some ways more dangerous. The anxiety of a nation that had just demonstrated unprecedented productive capacity and now faced the immediate strategic requirement of sustaining it, redirecting it, and accelerating it simultaneously. Between 1940 and 1945, American manufacturing output had undergone a transformation with few historical precedents. Automobile plants had been converted to tank and aircraft production within months. Shipyards had compressed multi-year construction timelines into weeks. The aluminum industry had expanded its smelting capacity by more than 400% in under 5 years. By 1944, the United States was producing more military aircraft per month than Germany and Japan combined. The industrial apparatus that accomplished this was vast, coordinated, and operating under conditions, wartime contracts, suspended labor regulations, concentrated federal investment, that could not be maintained indefinitely in peacetime. When the war ended in August 1945, the question facing American industrial planners was not whether capacity existed. The question was what that capacity would now be directed toward, and under what terms. The answer arrived in pieces and then all at once. The Soviet Union detonated its first nuclear device in August 1949, 4 years ahead of American intelligence estimates. 14 months later, North Korean forces crossed the 38th parallel. The brief post-war assumption that American technological supremacy would translate automatically into lasting strategic security collapsed within a single presidential term. What replaced it was something that would define American industrial policy for the next 3 decades: the permanent mobilization economy, a state of continuous, institutionalized military-industrial readiness that required not just existing manufacturing capability but expanding manufacturing capability, year over year, without interruption. For the metals industry, this had a specific material consequence. Aircraft were growing larger, faster, and structurally more complex. The jet age demanded airframes built from aluminum and titanium alloys engineered to tolerances that wartime production methods could not reliably achieve. More critically, the emerging missile programs, first the intercontinental ballistic missile projects of the early 1950s, then the space launch vehicles that followed, required structural components of a size and metallurgical specification that simply exceeded the capacity of any forge press then operating in the United States. In 1950, the largest hydraulic forge press in American operation exerted approximately 6,000 tons of force, a figure that sounds enormous until it is measured against what aerospace engineers were now specifying. The structural bulkheads, wing spars, and fuselage frames required for the next generation of aircraft and missiles demanded forgings that could only be produced under pressures 2, 3, and in some cases 5 times that figure. There was a gap, a precise, measurable, strategically critical gap, between what American forge capacity could produce and what American defense programs required. The federal government moved to close it with unusual directness. In 1950, the United States Air Force, working through the Defense Production Act and in coordination with the newly formed Munitions Board, initiated the Heavy Press Program, one of the least publicized and most consequential industrial investments in American history. The program's mandate was straightforward: finance the design and construction of forge presses and extrusion presses of a scale never previously attempted, install them at selected private manufacturing facilities, and make the resulting forging capacity available to defense and aerospace contractors on a priority basis. The budget allocated was substantial. The timeline was compressed. The engineering problems were considerable. And the question of what it would mean to station human workers beside machines of that scale, what it would ask of them, what it would do to them, was a secondary consideration, addressed in the program specifications at a level of attention that would later be described by industrial safety researchers as, at best, inadequate. The presses were built. They were built quickly. They were built large. And the men who would operate them were hired, trained in abbreviated programs, and placed beside them before the paint on the facility walls had fully dried. The engineering problem at the center of the heavy press program was not subtle. It was a problem of pure scale, of translating a well-understood mechanical principle, hydraulic force multiplication, into a physical structure large enough to exert pressures that had no industrial precedent, stable enough to maintain die alignment under those pressures, and durable enough to repeat the operation thousands of times without structural fatigue, introducing dimensional variance into the finished forgings. Hydraulic presses had existed since the early 19th century. Joseph Bramah had patented the foundational hydraulic press mechanism in 1795, and by the mid-1800s, hydraulic forging presses were operating in British and German steel mills. The principle was not in question. Pressurized fluid, confined in a cylinder and acting against a piston of defined area, multiplies applied force by a ratio directly proportional to the pressure generated and the piston cross-section. To achieve 50,000 tons of force, the upper range of the largest presses in the heavy press program required either enormous hydraulic pressure, enormous piston area, or both. The engineering answer pursued by the American program, working in close collaboration with German technical expertise acquired through post-war intelligence operations, was to build frames of a size and material mass that could absorb the reaction forces generated by the press cycle without deflecting. Because deflection, even microscopic deflection in the press frame, translated directly into dimensional error in the finished forging. Aerospace tolerances did not permit that error. The result was structures of almost geological proportion, The 50,000-ton press installed at Alcoa's facility in Cleveland and its twin at Wyman Gordon's plant in Grafton, Massachusetts, stood over 12 stories tall. Their frames were fabricated from steel forgings. The irony of requiring forge capacity to build forge capacity was not lost on the engineers involved, and their foundations extended more than 30 feet below the facility floor, anchored into bedrock with reinforced concrete caissons designed to distribute the press reaction load across an area measured in thousands of square feet. The hydraulic systems that powered them required pump stations the size of small buildings, capable of generating fluid pressures exceeding 5,000 pounds per square inch and delivering that pressure to the main cylinders through pipe manifolds with wall thicknesses measured in inches. The presses in the 2,000-ton class, smaller than the program's largest machines, but still representing the upper range of what most aerospace component suppliers would install, presented their own engineering challenges. At this scale, the machine was large enough to produce the structural forgings required for missile airframes and spacecraft structural members, but compact enough, if that word can be applied to a machine weighing 4 million pounds, to be installed in existing industrial facilities with reinforced foundations rather than purpose-built structures. The die systems used in these presses deserved particular attention because the die was where the machine's force met the material and where the most precise and most dangerous work occurred. A forged die for an aerospace structural component was itself a precision engineering artifact. Machined from H13 tool steel, a chromium molybdenum vanadium alloy capable of withstanding repeated thermal cycling without surface degradation, a single match die set for a major structural forging could weigh 40,000 pounds and require 6 months of precision machining to produce. The die cavity defined the finished geometry of the forging with tolerances measured in thousandths of an inch. Any contamination of the die surface, scale from an improperly cleaned billet, a fragment of lubricant that had carbonized at die temperature, a hairline crack propagating from a thermal stress point, produced a defective forging and, if not caught immediately, risked die failure under the next press cycle. Die failure at full press tonnage was not a gradual event. It was catastrophic and instantaneous. Tool steel fragments under those conditions did not fall. They moved at velocities comparable to low-velocity projectiles. The men who installed die sets, who cleaned die cavities between press cycles, who inspected die surfaces under the press while the ram was held in the raised position by hydraulic pressure alone. Those men understood this, in the way that proximity to a specific kind of danger produces a knowledge that no training manual fully captures. They understood it in their hands and in the particular quality of their attention when they were inside the press working area. The machine was commissioned. The production schedules were established. The contracts with airframe manufacturers and missile prime contractors were signed. And in the shift briefings conducted in the first weeks of operation, foremen told new operators what the floor trembling had already begun to communicate, that this machine would not negotiate with inattention, would not pause for hesitation, and would not distinguish between an aluminum billet and the hand of the man positioning it if the two occupied the same space at the moment the ram was released. Production began. The press ran 3 shifts. It ran every day. To stand beside a 2,000-ton hydraulic forge press and understand what you are looking at requires a deliberate act of cognitive reorientation. The human eye, trained by ordinary experience to read, scale through comparison with familiar objects, fails initially at the task. The machine does not look large in the way that a tall building looks large, because a tall building presents its scale vertically, against a sky that contextualizes it. The press presents its scale in all directions simultaneously, width, depth, height, and a quality of mass that is not quite visual at all but is felt through the floor, through the ambient vibration of the hydraulic pumps cycling in the adjacent pump room, through the air pressure that changes perceptibly when the ram descends and displaces the volume of atmosphere trapped between the die faces and the final inches of closure. The machine consists of 5 primary structural and mechanical systems, each of which represents a distinct engineering discipline, and each of which must function within tolerances that are simultaneously extremely tight and subjected to forces and temperatures that work continuously to degrade them. The first system is the frame. In a press of this class, the frame is a pre-stressed steel structure assembled from components so large that they arrive at the installation site by specialized heavy transport and are assembled in place rather than delivered complete. The uprights, the vertical columns that guide the ram and resist the horizontal components of the press reaction load, are typically fabricated from forged steel billets, stress-relieved after machining, and assembled with pretensioned tie rods that place the entire frame in a state of controlled compressive stress before a single press cycle is run. This pre-stress is not incidental. It is the engineering mechanism by which the frame maintains its dimensional stability under load. A frame that deflects under load is a frame that produces dimensionally inconsistent forgings. The pre-stress counteracts deflection by ensuring that the working loads never exceed the pre-applied compression, that the frame, in effect, never experiences net tension during operation. The second system is the hydraulic drive. At 2,000 tons of press force, the hydraulic system is operating at fluid pressures that require engineering solutions borrowed from the high-pressure pipeline and submarine pressure hull industries. The main cylinders, typically 2 to 4 in number, arranged symmetrically above the ram to ensure even load distribution, have bore diameters measured in feet. The seals that contain fluid pressure at these diameters are not off-the-shelf components. They are custom-engineered assemblies, manufactured to close tolerances, and subject to wear rates that make them one of the highest maintenance items in the entire system. A seal failure at operating pressure does not produce a slow leak. No, it produces a hydraulic fluid release at pressures sufficient to cut through unprotected human tissue with the efficiency of an industrial cutting tool. The third system is the die set and bolster assembly. The bolster, the massive steel table on which the lower die is mounted, is itself a precision-machined component, typically weighing between 20,000 and 60,000 pounds depending on press size, and equipped with a hydraulic die clamping system that must hold the lower die in precise registration under impact loads that occur at the moment of forging contact. The upper die is mounted to the ram face through an intermediate adapter plate, and the alignment between upper and lower dies, measured as the parallelism and concentricity of the matched die cavity surfaces, must be maintained within tolerances of a few thousandths of an inch across the full range of press operation. Any misalignment, whether from thermal distortion, mounting error, or frame deflection, produces a forging with a visible parting line offset that is both a dimensional defect and a stress concentration in the finished part. The fourth system is the thermal management infrastructure surrounding the press. Aluminum and titanium alloys must be forged within specific temperature windows, typically between 650 and 950 degrees Fahrenheit for aerospace aluminum alloys, and between 1,600 and 1,900 degrees Fahrenheit for titanium. Because the material's flow stress, the resistance it presents to plastic deformation, is strongly temperature dependent. Too cold, and the material does not flow completely into the die cavity, producing an incomplete forging, or, worse, a forging that appears complete but carries internal voids detectable only by ultrasonic inspection. Too hot, and the alloy's microstructure degrades, with grain growth and incipient melting at grain boundaries producing a part that meets dimensional specifications while failing the metallurgical ones. The furnaces that heat billets to forging temperature are located adjacent to the press, close enough that transfer time, the interval between billet extraction and die contact, does not allow excessive temperature loss, But this proximity means that the operators working the press floor are working in an environment where radiant heat from both the furnace doors and the heated billets contributes to ambient temperatures that, at the die face during active production, routinely exceed 110 degrees Fahrenheit. The fifth system is the control and safety interlock architecture. In the presses built during the heavy press program era, this architecture was electromechanical. Relay logic, limit switches, mechanical interlocks, rather than the programmable logic controller systems that would become standard in later decades. The safety interlock system was designed to prevent ram descent if specific conditions were not met. Die area clear, safety gates closed, operator controls in neutral position. In theory, the interlock system created a barrier between the press cycle and the possibility of human presence in the die area during closure. In practice, the reliability of electromechanical interlock systems in high-temperature, high-vibration, heavy industrial environments was a function of maintenance discipline and component replacement schedules. And the production pressures that characterized forge shop operations in the 1950s and 1960s created an institutional environment in which maintenance schedules were, with documented regularity, subordinated to production schedules. When an interlock failed, when a limit switch fouled with scale and lubricant, when a relay contact oxidized and produced an intermittent fault, when a safety gate sensor was defeated by an operator who had learned that the gate's closure added 40 seconds to a press cycle that management measured against a production quota, the engineered barrier between the press cycle and the human body in the die area became theoretical. The machine did not know the difference. The ram descended on schedule, at full tonnage, with the indifference of physics toward the biological. That indifference was the hidden variable in every production calculation conducted in every forge shop running machines of this class. It was present in the engineering specifications. It was present in the safety documentation. And it was systematically underweighted in the operational decisions made daily by the men who ran these facilities, because the production targets written into the defense contracts did not carry a line item for the cost of what happened when the indifference of the machine and the fallibility of the interlock system and the exhaustion of a man on his 11th hour of a 12-hour shift occupied the same moment in time. Every complex industrial system contains a category of risk that does not appear in its design documentation, not because the engineers who produced that documentation were negligent, but because the documentation describes the system as designed, and the risk in question belongs to the system as operated. The gap between those two descriptions is where industrial accidents live. In the 2,000-ton forge press, that gap had several specific dimensions. The first was thermal fatigue in the die system. Tool steel dies operating in the temperature cycling regime of active aerospace forging production, heated by contact with billets at 700 degrees, cooled by die lubricant spray between cycles, reheated on the next cycle, experienced a thermal fatigue mechanism that the metallurgical understanding of the early 1950s had not fully characterized. The surface layer of the die, the first few millimeters of H13 tool steel that formed the actual die cavity, underwent repeated expansion and contraction at a frequency and magnitude that generated compressive and tensile stress cycles at the surface. Over time, these cycles initiated a network of fine surface cracks, heat checking, that in early stages was cosmetically objectionable but structurally tolerable, and in later stages represented a progressive degradation of the die's structural integrity. The problem was that the transition between those two stages was not visually obvious. A die face exhibiting heat checking at a level that still fell within accepted production parameters looked, to an operator conducting a visual inspection between press cycles, very similar to a die face that had crossed the threshold into the range where a forging stroke could propagate one of those surface cracks through the die body and produce a catastrophic tool failure. The inspection techniques available to press floor personnel in the 1950s and 1960s, visual examination, occasionally supplemented by die-penetrant testing when the foreman authorized the production delay that testing required, were inadequate to reliably distinguish between the two conditions. The second dimension of the gap concerned the behavior of the aluminum billet during the forging stroke itself. When a heated billet is placed in the lower die cavity and the ram descends, the material does not flow uniformly and predictably in all cases. If the billet temperature is uneven, hot at the surface from furnace exposure, cooler at the core, the outer material flows readily while the core resists, creating internal stress distributions that are not reflected in the die fill pattern visible at the parting line. If the billet is positioned with even slight angular misalignment relative to the die cavity, the initial contact geometry creates asymmetric lateral loads that the die clamping system must absorb. These asymmetric loads, if they exceeded the clamping force, they produced a lateral displacement of the lower die, a phenomenon called die shift, that was detectable only by dimensional inspection of the finished forging, by which point the press had already completed the stroke. Die shift was a production quality problem, but it was also a safety problem because a lower die that had shifted under the previous stroke was, if not detected and corrected, misaligned for the next stroke. And a misaligned die-produced asymmetric flash, the thin fin of excess metal extruded at the die parting line, that could be ejected laterally from the die area at the moment of maximum press tonnage with sufficient force and temperature to cause burns and lacerations to personnel within several feet of the press. The third and most consequential dimension of the gap was the one that cannot be located in any blueprint, because it existed not in the machine, but in the organizational system surrounding it. The production quotas written into defense contracts in the 1950s and 1960s were not suggestions. They were contractual obligations, tied to payment schedules, subject to penalty clauses, and monitored by government procurement officers whose performance evaluations were partly a function of whether the programs they managed stayed on schedule. The forge shop managers who operated these presses were caught between two systems of accountability: a safety system that required press downtime for maintenance, for die inspection, for interlock testing, and for operator fatigue management, and a production system that treated downtime as a cost to be minimized and schedule slippage as a failure to be avoided. When those two systems came into direct conflict, when a maintenance interval was due but a production deadline was closer, the resolution of that conflict was not random. It followed the organizational gradient. It followed the direction in which consequences were most immediate, most quantifiable, and most visible to the people making the decision. Maintenance could be deferred. A delivery date could not. This pattern was not unique to forge shops. It has been documented across American heavy industry in the post-war period, and it has been analyzed extensively in the industrial accident literature that emerged following the major regulatory reforms of the early 1970s. But in the forge press environment, the pattern had a particular lethality because the consequences of deferred maintenance in this specific system were not gradual. They were not telegraphed by slowly declining performance indicators. They arrived suddenly, at full press tonnage, in the fraction of a second that the ram required to travel its final inches of stroke. The blueprints described a machine. They did not describe the environment in which the machine would be operated, the pressures that would govern decisions about its maintenance, or the consequences that would be distributed, unequally, invisibly, and without formal acknowledgement, among the men stationed beside it when those decisions resolved against them. That omission was not an oversight. It was a structural feature of the system that built the parts that flew to space. The shift begins at 5:45 in the morning, 15 minutes before the official start time, because arriving at 5:45 is what the foreman expects and what every experienced operator in Bay 7 understands without being told. The extra 15 minutes are not paid. They are the unofficial currency of workplace standing, the visible demonstration that a man takes his position seriously enough to give something beyond what the contract requires. By 5:50, the bay is populated with 12 men performing tasks that do not appear in any job description. Die surfaces are being examined by flashlight, the beam held at an oblique angle to the tool steel face to catch the shallow topography of heat, checking that overhead lighting flattens into invisibility. The hydraulic system pressure gauges are being read and logged in a notebook that one of the senior operators keeps in his chest pocket, a personal record accumulated over 4 years that does not duplicate and in several respects contradicts the official maintenance log kept in the foreman's office. The billet furnace, which has been running since 2 in the morning under the supervision of the night crew, is being checked for temperature uniformity by a man who inserts a long-handled optical pyrometer through the furnace door and reads the surface temperature of each billet in the charge, with the focused attention of someone for whom this reading is not a procedural formality, but a direct input to a personal risk calculation. These men are not young. The forge press industry in this era does not place inexperienced workers in primary operator roles on large hydraulic presses, because inexperience in this environment is not corrected by instruction. It is corrected by incident, and the incidents on a 2,000-ton press are not instructive. The senior operator on the morning shift has 11 years of forge press experience. He is 43 years old and moves with the particular economy of motion that develops in men who have worked for years in spaces where unnecessary movement consumes energy that is not recoverable by any means available on the press floor. He carries the accumulated knowledge of 11 years of this specific machine in his body, in the calibration of his hearing to the hydraulic system's normal sound signature, in the tactile memory of how the ram's approach feels through the floor at different press speeds, in the practiced spatial awareness that allows him to know, without looking directly, where every other person in his immediate work area is positioned at every moment of the press cycle. His name does not appear in the production records that were preserved. The records that were preserved document tonnage, cycle times, die change intervals, and forging rejection rates. They document the machine. The men who operated it were recorded, when they were recorded at all, in a separate filing system, the personnel records, the workers' compensation filings, the incident reports, that was maintained in a different office, by different people, for different institutional purposes, and that was not considered relevant to the performance history of the press. The work itself, on a morning when production is running cleanly and nothing has gone wrong, is a choreography of coordinated movement between the press operator, the manipulator operator, and the die area attendant. 3 men whose actions must be synchronized to a press cycle that, at production speed, completes in under 60 seconds from billet placement to forging ejection. The manipulator operator extracts a heated billet from the furnace using a set of hydraulic tongs mounted on an overhead rail system and transfers it to the lower die cavity. Transfer time is critical. Every second of exposure to ambient air after furnace extraction costs the billet surface temperature at a rate that varies with billet geometry and alloy composition, but averages between 5 and 15 degrees Fahrenheit per second. A billet that arrives at the die face 15 seconds late may be 30 degrees below the optimal forging temperature at its surface, and the operator cannot see this. He can only know it from experience, from the number of billets he has transferred and the number of press cycles he has watched, and the accumulated pattern recognition that tells him when a billet looks right and when it does not. When the billet is positioned, the press operator initiates the cycle from a control station located to the side of the press frame, outside the die area perimeter defined by the safety gate system. He does not watch the die area during the stroke. He watches the pressure gauges. He watches for the pressure curve that tells him the material is flowing correctly, the characteristic profile of rising pressure as the ram contacts the billet, the plateau, as the material yields and fills the die cavity, the final pressure spike as the flash forms at the parting line and the stroke reaches its programmed stop point. Any deviation from that expected curve, a premature pressure spike indicating a cold billet or a mispositioned one, an absent plateau indicating a billet of incorrect weight, is information that he processes in real time, with the option to abort the stroke within a window measured in fractions of a second. He does not always have that fraction of a second. There are days when everything in the system is functioning within specification, when the temperature readings are correct and the die surfaces are clean, and the interlock system responds exactly as designed, and the press cycles 60 times in an hour, and at the end of the shift the finished forgings are stacked on the inspection table, and the dimensional checks come back clean, and the parts are tagged and moved to the shipping area. And everything that was supposed to happen happened exactly as it was supposed to happen. There are other days. On the other days, the sequence begins the same way, the floor trembling, the hydraulic pumps cycling, the furnace heat pushing against the back of the neck, and somewhere inside that sequence, something deviates. Sometimes the deviation is recoverable. Sometimes a man is fast enough or positioned correctly or simply fortunate in the geometry of what goes wrong. Sometimes the machine does not distinguish between the billet and the hand of the man who placed it. The senior operator in Bay 7 has watched both kinds of days accumulate across 11 years. He knows the ratio. He knows what the ratio means. He comes to work anyway at 5:45, 15 minutes before his shift begins, and he checks the die surface with a flashlight held at an angle that catches what the overhead lights miss. Because that is what the job requires, and because he is, in the most precise sense of the term, a professional. The language of industrial accident documentation is a language designed, whether intentionally or by institutional evolution, to absorb human catastrophe without transmitting its full weight to the reader. An operator sustains a crush injury to the right hand. A worker is treated for thermal burns to the forearm and returned to modified duty. A press cycle is interrupted following contact between personnel and moving equipment. The passive construction, the clinical terminology, the bureaucratic framing, these are not accidental features of the documentation. They are the form that institutional self-protection takes when it is required to acknowledge that something terrible happened, while simultaneously containing the acknowledgement within language that does not invite further inquiry. Behind that language, in the forge shops operating 2,000-ton class presses across the American industrial belt between 1955 and 1972, there is a different record. It exists in fragments, in the testimony collected by union safety committees that were denied access to company incident files, in the oral accounts preserved by the United Steelworkers of America and the International Brotherhood of Boilermakers in regional archives that have received little scholarly attention, in the personal injury litigation records of county courts in Ohio, Pennsylvania, and California, and in the private correspondence of industrial physicians who worked under contract to forge shop operators and who wrote to colleagues and occasionally to regulatory bodies, with a candor that their employment agreements did not technically permit. That record describes a pattern. The pattern begins not with the catastrophic incidents, the ones that produced fatalities or injuries severe enough to trigger mandatory regulatory reporting, but with the incidents below that threshold, the incidents that were handled internally, the burns treated in the company medical office and recorded as minor thermal contact without further specification, the crush injuries to fingers and hands that were classified, when the damage did not result in amputation or permanent disability exceeding a defined threshold, as recordable but not reportable to the regulatory bodies that existed before OSHA's creation in 1970. The near misses, the moments when the geometry of what went wrong resolved in the direction that left the man standing, that were not recorded at all, because there was no regulatory requirement to record them and every operational incentive not to. A union safety representative working at a forge facility in northeastern Ohio during the early 1960s maintained his own log. He kept it in a composition notebook, updated after every shift, recording the incidents that the official system did not capture. Over a period of 4 years at a single facility operating 2 large hydraulic forge presses, his log documents 47 incidents involving unplanned contact between press personnel and hot material, moving equipment or press components, contacts that resulted in injuries ranging from minor burns to a crush injury requiring the surgical amputation of 2 fingers. Of those 47 incidents, 11 appear in the facility's official incident log. The remaining 36 do not. This is not an anomaly. It is, based on the available comparative evidence from multiple facilities and multiple time periods, a representative ratio. The catastrophic incidents, the ones that could not be contained within the internal reporting system, have a different character. They are fewer in number and vastly greater in consequence, and they share a structural feature that the incident investigations, when investigations were conducted, consistently identified and consistently failed to act upon in any systemic way. In the spring of 1961, at a forge facility in the Los Angeles basin, operating a press in the 2,000-ton class under contract to a major airframe manufacturer, a die change operation went wrong in a sequence that the subsequent investigation reconstructed with considerable precision. The upper die, a matched component weighing approximately 18,000 pounds, was being lifted from the ram face by an overhead crane following a production run. The die lifting fixture, a custom fabricated assembly of alloy steel hooks and connecting hardware, had been in service for 3 years. It had not been inspected on the schedule specified in the facility's maintenance documentation. One of the primary load-bearing hooks had developed a crack, originating at a stress concentration point at the inner radius of the hook that had propagated through approximately 60% of the hook's cross-sectional area without producing any external indication visible during a routine visual inspection. When the crane lifted the die, the hook failed. The die fell. 2 men were in the die area conducting the change operation. One moved. One did not move quickly enough. The investigation report, filed with the California Division of Industrial Safety, runs to 22 pages. It identifies the proximate cause as a fatigue failure in the lifting fixture. It recommends enhanced inspection intervals for lifting equipment. It does not examine the organizational conditions under which the inspection schedule had been allowed to lapse. The production pressures, the maintenance resource constraints, the institutional prioritization that had placed the die change crew in the die area with lifting equipment that had not been verified as safe for the load it was being asked to carry. The facility resumed production 11 days later. The parts it was producing, structural forgings for a missile program then in active development, were on a delivery schedule that a defense procurement officer had characterized, in internal correspondence, as having no acceptable margin for delay 11 days. In the years that followed, the pattern repeated at other facilities with variations in the specific mechanism, but consistency in the structural conditions that produced it. An interlock system bypassed because a faulty limit switch had been generating false stops, and the repair parts were on a 3-week lead time, and the production schedule did not have 3 weeks. A billet transfer conducted with 1 fewer operator than the task required, because 2 men were out sick and management had not authorized overtime for a replacement. A die inspection deferred because the die penetrant testing kit was depleted, and the requisition for replacement materials had not been approved. Each of these decisions, made individually by individuals operating within an institutional system that structured their options and weighted their incentives, was defensible in isolation. Each of them, in the particular combination that characterized the moments when things went irreparably wrong, contributed to an outcome that the system then processed through its documentation mechanisms and returned to the production floor, adjusted by exactly the minimum required by regulatory compliance, and no further. The men who were injured in these incidents did not, as a general matter, speak publicly about what had happened to them. Some were bound by settlement agreements that included confidentiality provisions. Some were dependent on their continued employment at the facility where the injury had occurred, and understood that public statements about workplace safety conditions were inconsistent with continued employment. Some had internalized, across years of working in an industry that treated stoicism as a professional virtue, a disposition against complaint that was indistinguishable from the disposition of a man who believed that what had happened to him was simply the cost of the work. And the work continued to be necessary. The contracts continued to specify the forgings. The forgings continued to require the presses. The presses continued to run 3 shifts. The floor continued to tremble before the machine moved. In the summer of 1969, when the Saturn V rocket carrying Apollo 11 cleared the launch tower at Kennedy Space Center and began its trajectory toward a lunar insertion orbit, the structural members bearing the primary loads of that ascent had a history that no mission profile document recorded and no television broadcast described. They had been heated in furnaces, transferred by men with hydraulic tongs, placed in die cavities, and compressed under pressures measured in tens of thousands of pounds per square inch. They had been produced on forge presses operating in facilities that smelled of hot metal and hydraulic fluid, and the particular industrial lubricant, a graphite-based compound applied to die faces between cycles, whose smell, men who worked in forge shops for any length of time reported, could never be entirely separated from the memory of the work itself. The connection between the forge press and the space program was not incidental or peripheral. It was load-bearing in the most literal structural sense. The Saturn V's first stage, the SIC, generated 7.6 million pounds of thrust at liftoff and transmitted those loads through a thrust structure, a complex of frames, rings, and longitudinal members that had to maintain its dimensional and structural integrity under dynamic loading conditions that ground testing could approximate but not fully replicate. The material specifications for those structural members required aluminum alloy forgings of a size and metallurgical quality that only large hydraulic forge presses could produce. The same was true of the S2 second stage, of the instrument unit ring that housed the Saturn's guidance systems, and of the structural elements of the Apollo Command and Service Module. NASA's material procurement specifications for primary structural forgings in the Apollo program, documents maintained in the Marshall Space Flight Center Technical Library, specified not just dimensional tolerances and alloy composition, but the forging process parameters themselves, the temperature windows within which the billets must be worked, the reduction ratios that must be achieved in the forging stroke, the post-forge heat treatment sequences that developed the final mechanical properties of the finished component. These specifications were written by metallurgists who understood that the forging process, correctly executed on a press of adequate capacity, produced material properties unachievable by any other manufacturing method. The structural advantages of forging over alternative manufacturing processes for aerospace primary structure are not marginal. A forged aluminum component, compared to a machined plate or an investment casting of equivalent alloy and geometry, exhibits a fatigue life that can be 2 to 3 times greater under cyclic loading conditions. This advantage derives directly from the grain flow modification that the forging process produces, the realignment of the alloy's internal grain structure along contours that follow the finished part geometry rather than crossing it, eliminating the grain boundary intersections at the part surface where fatigue cracks preferentially initiate. For a structure subjected to the vibration environment of a rocket launch, the acoustic loading from 7.6 million pounds of thrust, the combustion, instability-induced pressure oscillations, the aerodynamic buffeting of transonic flight, that fatigue life advantage was not an engineering preference. It was a mission requirement. Components that failed under cyclic loading did not fail gradually. They failed in the way that aluminum alloy structural members under high cycle fatigue always fail. Suddenly, completely, and without warning sufficient to allow any corrective response. The men at Wyman Gordon's Grafton facility, at Alcoa's Cleveland operation, at the forge shops in California supplying the airframe manufacturers who were themselves supplying NASA prime contractors. Those men knew none of this in the specific technical terms that the NASA metallurgists used. What they knew was that the parts they were making were important, that the inspection requirements were more rigorous than anything they had previously worked to, and that the rejection criteria applied to aerospace forgings were unforgiving in ways that commercial or military production had not always been. They knew this because the parts that were rejected, the forgings that came back from ultrasonic inspection with internal indications, or from dimensional inspection with out-of-tolerance features, or from visual inspection with surface conditions that did not meet specification, were not reworked and resubmitted in aerospace production the way they might have been in other manufacturing contexts. They were scrapped entirely. The metallurgical requirements were binary. The part either met specification or it did not, and if it did not, it was removed from the production stream and destroyed, and the press cycle that had produced it was analyzed to determine whether the process parameters had deviated from specification and whether the deviation represented a systemic condition requiring correction. This quality discipline was, by the standards of 1960s American manufacturing, exceptional. It reflected NASA's understanding, developed painfully through the failures of early unmanned programs, and that in a launch vehicle carrying human beings, the failure of a single structural component was not a local event. It was a mission event, potentially a fatal one. The parts that passed inspection, the forgings that met every dimensional, metallurgical, and surface condition requirement, were tagged with material certification documents that traced them through every stage of production, from the original aluminum ingot through the forging operation, through heat treatment, through final inspection. Those documents traveled with the parts through the supply chain, through the assembly process, and into the final vehicle configuration records that NASA maintained for every Apollo mission. The men who made those parts are not named in those records. The records document the material, the process, the inspection results, and the certification. They do not document the 11-year veteran who checked the die face with a flashlight at 5:45 in the morning, or the manipulator-operator who learned to read a billet's temperature by its color in the furnace's ambient light, or the men who absorbed in their bodies the risks that the production system had determined were acceptable in exchange for parts that flew. They made those parts. The parts flew. Neither fact cancels the other. The Occupational Safety and Health Act was signed into law on December 29, 1970. It was not a sudden legislative response to a sudden crisis. It was the accumulated consequence of 2 decades of industrial injury data, labor union advocacy, and a growing body of occupational medicine research that had been making the same argument in progressively less deferential terms, that the American industrial system was externalizing a category of cost, the cost of worker injury, disability, and death, onto the workers themselves and onto the public programs that supported them, while the production gains generated by the conditions that produced those costs were retained entirely within the private accounting of the firms that operated the facilities. The forge press industry did not greet the act with institutional enthusiasm. The specific regulatory requirements that OSHA introduced for forge shop operations, requirements governing point of operation guarding on mechanical presses, requirements for regular inspection and certification of lifting equipment, requirements for environmental monitoring of heat stress conditions, requirements for maintenance documentation that could be audited by compliance officers. Each of these represented a direct cost to operations that had previously absorbed those costs only when an incident made absorption unavoidable. Installing guarding systems on presses that had operated without them required capital expenditure. Conducting heat stress monitoring required personnel and equipment. Maintaining auditable maintenance records required administrative infrastructure and, more importantly, I required that deferred maintenance become visible to external review in a way that internally managed records had never been. The industry's response followed the pattern that regulatory historians have documented across American heavy industry in the early OSHA period. Initial resistance, conducted through industry associations and direct lobbying, focused on the compliance cost argument, the position that the regulatory requirements were economically disproportionate to the safety benefits they would produce, measured in a cost-benefit framework that assigned monetary values to human injury and death derived from workers' compensation settlement data rather than from any more expansive accounting of human cost. When resistance failed to prevent the regulations from taking effect, compliance became selective, focused on the requirements most easily verified by compliance inspectors and least attentive to requirements that were difficult to inspect or that carried lower penalty exposure. The men who had been injured in the years before OSHA's creation received nothing from the Act's passage that addressed the injuries they had already sustained. The settlements they had accepted, in many cases under financial pressure, in some cases with confidentiality provisions, in nearly all cases for amounts that reflected the depressed value that the workers' compensation system assigned to the permanent impairment of a working-class body, were not revisited. The institutional record of what had happened in Bay 7 and its equivalents across the industrial belt remained distributed across filing systems that were not connected to each other, not accessible to researchers, and not considered relevant to the forward-looking compliance framework that OSHA's enforcement mechanism created. The cost ledger, in other words, was never fully compiled. The production side of it and the tonnage, the contracts, the delivery schedules met, the aerospace program supported, existed in records that were preserved because they documented organizational achievement. The injury side of it existed in records that were preserved, when they were preserved at all, because regulatory compliance required it, and in formats that made aggregation across facilities and time periods a task requiring archival research that has still, decades later, not been comprehensively undertaken. What the available evidence supports is a conservative estimate. Across the facilities operating large hydraulic forge, presses under defense and aerospace contracts between 1955 and 1975, the documented injury rate in forge shop operations consistently exceeded the manufacturing sector average by a factor of between 2 and 4, depending on the facility, the press class, and the period examined. Crush injuries and thermal burns accounted for the majority of serious incidents. Fatal incidents were less frequent but not rare, occurring at a rate that, distributed across the workforce employed in this specific operation over this specific period, represents a human cost that no production record acknowledges. The silence around that cost was not uniform. The United Steelworkers, in particular, maintained safety committees that documented conditions and advocated for improvements with persistence that the documentary record reflects clearly. Individual workers filed complaints, gave testimony, wrote letters. Industrial physicians published findings. Labor journalists reported incidents when they could obtain documentation. The silence was not the silence of absence. It was the silence of a system in which the channels for making this information consequential were systematically narrower than the channels for processing production output, and in which the institutional weight on the production side of the ledger continuously exceeded the institutional weight on the human side. That asymmetry did not end with OSHA. It evolved. It became more sophisticated in its mechanisms and more legible in its language. But the structural condition it expressed, the condition in which the human cost of producing necessary things is distributed among those least positioned to resist that distribution, did not resolve. It persisted in the forge industry and beyond it as a feature of the system rather than a correctable flaw within it. Metal remembers. This is not a metaphor. It is metallurgy. The grain structure of a forged aluminum component, the internal architecture produced by the press stroke, by the temperature at which the billet was worked, by the reduction ratio achieved in the die cavity, is permanent. It does not relax. It does not revert. Decades after the forging operation, a cross-section of the finished part, examined under a metallographic microscope, still shows the grain flow lines laid down in the seconds of the press cycle. The material carries the record of its own making in its internal structure, invisibly, permanently, in a language readable only by those trained to look for it. The men who made it do not have an equivalent permanence in the institutional record. Their names are not on the parts. Their names are not in the production logs that documented the tonnage and the cycle times, and the die change intervals. Their injuries, the ones that were recorded, exist in filing systems that are, in most cases, no longer actively maintained, in formats that do not permit the kind of aggregation that would allow a complete accounting of what the forge press cost in human terms across the 2 decades of its most intensive operation. What persists, in the absence of that complete accounting, is the work itself. The Apollo program succeeded. That success was real, and its material foundation was real, and the forge pressings that formed part of that foundation were real components that performed as specified under conditions that tested them completely. When the Saturn V's first stage engines ignited and the vehicle cleared the tower and the acoustic energy of 7.6 million pounds of thrust rolled outward across the Florida marshland, the structural members carrying those loads held. They held because the men who made them understood, at a level of professional knowledge that no job description fully captured, how to read a die face in oblique light, how to judge a billet's temperature by its color, how to operate within a system that demanded more than it acknowledged and gave back less than it took. That knowledge was not theoretical. It was embodied, carried in hands that knew the weight and heat of the work, in ears calibrated to the hydraulic system's normal sound, in the practiced spatial awareness of men who had learned to exist safely beside a machine that did not share their interest in their survival. Some of those men were damaged by the machine they mastered. Some were damaged in ways the record documents, and some in ways it does not. The cumulative hearing loss from years of forge shop noise levels, the chronic musculoskeletal conditions from the physical demands of the work, the psychological residue of proximity to industrial violence that the occupational medicine of the era did not recognize as an injury category and therefore did not treat as one. They were not, in the main, celebrated. The culture of American industrial labor in this period did not tend toward celebration of its own participants. It tended toward production, toward the next shift, the next contract, the next delivery. The men who operated the forge presses understood this. They understood that the institution they worked within valued what they produced more completely than it valued them, and most of them had arrived at an accommodation with that understanding that allowed them to continue doing the work with the professionalism the work required. That accommodation was not resignation. It was something more considered, a decision made with full knowledge of its terms to bring skill and care and professional discipline to a set of conditions that had not been designed with their welfare as a primary constraint. It was a decision that deserves more than the silence that the institutional record has mostly returned to it. The presses still exist, some of them. The largest survivors of the heavy press program, the 50,000-ton machines at Alcoa and Wyman Gordon, were still operating into the 21st century, producing forgings for aerospace programs whose material requirements had not changed in their fundamental character since the Apollo era. The 2,000-ton class machines that formed the production backbone of the 1960s aerospace supply chain have mostly been replaced by newer equipment, more instrumented, more automated, with control systems that have reduced the proximity of human operators to the die area and expanded the interlock architectures that stand between the press cycle and the human body. The risk has not been eliminated. It has been engineered to a lower level, which is the most that can be said for any industrial process operating at this scale. Men still work beside these machines. The floor still trembles before the ram descends. What has changed is the accounting, or rather, the aspiration toward a more complete accounting. The regulatory framework that OSHA created, imperfect and unevenly enforced as it has been, established the principle that the cost of industrial production must include the cost of the human beings who perform it, that this cost cannot be externalized indefinitely without consequence, cannot be absorbed silently into workers' bodies and workers' compensation settlements and institutional silence, and still be called an acceptable arrangement. That principle has not been fully realized. The gap between its statement and its implementation remains wide, measured in injury statistics that still exceed what a complete accounting would permit, in enforcement resources that still fall short of what the regulatory mandate requires, in organizational cultures that still resolve the conflict between production pressure and safety margin in the direction that the heavy press program's forge shops resolved it 60 years ago. But the principle exists. It was bought, in part, by the men in Bay 7, by the incidents that accumulated until they could no longer be entirely contained within the internal reporting system, by the union safety representatives who kept their own notebooks because the official notebooks could not be trusted, by the industrial physicians who wrote with candor that their employment agreements did not technically permit, by the workers who filed complaints and gave testimony and wrote letters into a system that processed their words slowly and incompletely, and returned, in most cases, something less than justice. The Saturn V flew. The Apollo missions achieved what they were designed to achieve. Those achievements belong to the engineers who designed the systems, to the astronauts who flew them, to the program managers who held together an enterprise of extraordinary complexity under extraordinary pressure, and to the industrial workers, the welders and machinists and press operators and die setters and furnace operators, whose labor made the physical objects that carried human beings to another world and returned them safely to this one. The metal they forged remembers the making. It is time that we remembered the makers.